Good afternoon, ladies and gentlemen. As I was introduced, I'm Aleksander Kauch. I'm lead gameplay programmer at 11-Bit Studios. I've worked on Frostpunk, on This War of Mine, and on the Anomaly series back years ago. And today I would like to introduce you to the topic of artificial intelligence in computer games, how it's implemented, what is its role in gameplay, and give you the general idea how it's done and how we do it in 11-Bit Studios. Okay, first of all, what is intelligence? There is no strict definition. I mean, scientific researchers does not agree on what intelligence is. Here you've got some examples of the definitions, and for the sake of this presentation and in gaming in general, the last one, so goal-directed adaptive behavior, is the definition that is closest to video games, because it just means that we have our goals and we try to adapt to the surroundings, to our surroundings, and to use it to our advantage to reach the goal. And artificial intelligence its definition is not strict also. So some say it's science of rational computer behavior or mimicking human intelligence, or just a study of some computational models that allows analyzing data and reasoning and so on. And once again, the last definition would be the definition that I would use for video games, because it's about analyzing the surroundings of AI agent and get a response from that AI system. And we put artificial intelligence into practice. We get something like this. But to be serious, it's widely used by Google, for example, Google Translate or internet web searches, image recognition software, some expert systems that help with the advisor that advise experts with their tasks. It's pretty hot topic right now in the industry, like in general IT. But in video games, starting with something very simple like a game of checkers, there is no need for artificial intelligence in checkers, because checkers is a solved game, which means there is an algorithm that always wins or ties with the player depending on who is the first player. So there is no need for intelligence. You just need to follow an algorithm and you always win or tie. In chess, however, the artificial intelligence already beats the best chess players. Like in 1997, the Deep Blue beat Garry Kasparov. And as far as I know, you can have almost grandmaster level intelligence on your mobile phone to play chess with. But the game is not solved. It always needs some kind of intelligence to play. There is no set algorithm to win every match of chess, and we are very far from finding that algorithm. It probably exists, but it's very complicated. But in video games, let's start with something very, very simple. And intelligence in Pong, it is very simple to write an intelligence that always wins. An opponent's palette could just move to the point where the ball will be hitting, and that's all. The computer always wins. But does not make very much sense, because we want the player to be challenged, but we must allow him to win sometimes. So the AI player is restricted by this maximum speed of the palette. It can try to reach the point where the ball will hit, but the limited speed limits the palette. In PacMan, it is extremely easy to write artificial intelligence so that the computer player always wins. You just need to write an algorithm that always follows PacMan. The ghost will follow PacMan, and if they pick different routes, the player has no chance to win, so the computer player always wins. But that doesn't make any sense, so instead, the developers of PacMan implemented 4 types of ghosts. The red one always tries to follow PacMan, the pink one tries to be ahead of PacMan, the blue one tries to get PacMan between the blue one and red one, and the orange is the most interesting because he just roams and does not care about PacMan. So if you run into a orange ghost, you are very lucky because he just doesn't care. Some conclusions. In some cases, we can write really simple artificial intelligence that always wins with the players. But that's not what the game is about. The game is about being challenging, being fun, and allowing the player to win. So it's not about writing the best intelligence that always wins with the player. In more complicated games like Warcraft, for example, RTS games, it is harder to write an intelligence that always wins. With older RTS, they used some tricks just to make the player challenged. So the AI player had infinite resources. They only sent waves of enemies at the player. And with some target prioritization, it already gave a challenge, but it was heavily scripted. Right now, of course, the RTS intelligence is more advanced, but still we do not have computational ability to write intelligence that always wins, for example, in StarCraft. In Call of Duty, the opponents have very simple default AI, but all the events, all the more complicated events are heavily scripted. They do not depend on the intelligence of the AI agents, they just follow a scenario, just to make the player feel like they're at war and everything is happening, and to give the player a feeling that he is participating in something important. So the level of artificial intelligence is not really connected with the difficulty in game, because Skyrim has a lot of complicated AI behaviors, and the characters in Skyrim try to mimic real life, and the game is very simple. There's almost no challenge, in my opinion, in Skyrim compared to Dark Souls, where the artificial intelligence is simplistic, even there is non-existent artificial intelligence at all, but the game is very challenging. So it's not always the level of AI that defines difficulty in game. And the conclusion of all these examples is that the only purpose of artificial intelligence existence in game is to keep the player entertained. And it depends on the game what that means. If you have a simple game with simple AI, but it's still challenging to the player, it's fine. If for the entertainment of the player you need a complicated behaviors, artificial intelligence behaviors, like in Skyrim, like in Fear, for example, if you remember the game, then go for it. But always remember that you are not writing, in most cases, you are not writing an opponent that always wins and always has to win, but you are making a game that should be playful and that should entertain the player. And how it's done. The first simple, naive way of writing artificial intelligence is just write some source code with some conditions, and you will have some conditions that check the state of the game, and write hard code the reaction. The problem is that everything is programmer dependent, and that example here is very simple, but when you get to more complicated examples, it does not look very simple at all. And that's just checking, do I have to attack someone or run away? Very simple behavior, a lot of code. So they are often used in very simple parts of artificial intelligence, hard-coded parts. They have have that way have a disadvantage of always needed to be written by a programmer. The programmer always has to participate in the process of creating artificial intelligence. It's still used in simple combat games like JRPG games, like, for example, Darkest Dungeon. It's not JRPG, of course, but the combat system is JRPG-like. It's usually written in script languages. And of course, if the programmer is smart and divides the code into function, it does not look that way, it looks better, of course. But still, it's hard to maintain, and when the AI system grows, it is almost unbearable. It cannot be developed any further. But, for example, this is Final Fantasy VII Bomb AI. It is written in Lua, scripting language with some modifications from Square. It's, I think, very simple behavior, but the combat in Final Fantasy VII is deep, but in the terms of AI, it's very simple. So it worked for them. But when you want to think about AI that can be developed by designers and only some parts of it implemented by programmers, we need some more sophisticated systems, sophisticated ways of writing the code. And one of the simplest tools is heuristics. Heuristic is a function that evaluates, for example, game state and put an answer of a number, for example, or like, am I in good state or bad state, or what should I do? The simplest algorithm that use heuristics is a star algorithm that is used to find the shortest path. The heuristics is the thing that differs A star from Dijkstra, because Dijkstra always searches every single possibility, and A star searches the most promising ones. So we evaluate the position and think, oh, I'm in the forest, let's go another way. With Dijkstra, you search all the way through the graph. And with that kind of evaluating function, we can move to goal-oriented action planning, GOAP. GOAP algorithms are the idea behind them is that AI has a very specific goal to reach. For example, get wood. And we have a set of actions that are the means to achieve the goal for the AI. So in our example of getting wood, the actions would be get tool, find forest, chop tree. And AI has a wide variety of actions to choose from and evaluates each chain of actions and picks the best sequence of actions with every action evaluated by some heuristics. So we find the shortest best path of single actions to reach the goal. Cost evaluation of each action is arbitrary. We need to implement how it's evaluated. Adding new actions only changes the amount of actions that needs to be checked. It does not break the algorithm. It does not change the rest of the algorithm. Everything should work fine with added actions. And every action can be a small GOAP system itself. So, for example, when we are talking about getting wood, finding a tool might be a GOAP subsystem of itself. So we need to find a shed, we need to pick up the axe, we need to get back to where we started. Where it was used, I think the best example would be Sims, where our Sims have their needs. For example, if our Sim needs to eat something, his chain of action would be go to the kitchen, make himself a sandwich, eat a sandwich. That's the actions that can be performed, and adding a new action would add, for example, a barbecue, another way of getting food. Another tool in AI toolset is finite state machines. In general, it's very basic computing mechanism that is the foundation of Turing machine and so on and so on. Basically, all the computing we have, but in terms of artificial intelligence, the most important thing is that we are always at one chosen state, and we have some actions that allow us to change the state. For example, if you see the turnstile here, we start at the state locked, and when we push the turnstile, it still remains locked. But when we use a ticket, it becomes open. When we use another ticket, it stays open, but when we push and go through, the turnstile will lock itself. That's the simplest finite state machine. AI is always in one state. For example, in combat, researching, searching for food, whatever you call it. Changing the state is only possible via the set transition table, via certain set of actions. State and transitions are highly parameterizable by designers, so the programmer does not have to implement everything. Some parts of it can be parameterized by designer, which is always good because it's their job to create artificial intelligence. But it still is programmer heavy technique. And the last and most sophisticated way of implementing AI, which emphasizes all of the above, and was used in this war of mine as well as in Frostpunk, is behavior trees. Behavior trees develop from the concept of hierarchical finite state machines. What is hierarchical finite state machine? We have a state of combat, and the combat is controlled by another state machine inside. With sword fighting is another finite state machine, with gunfight it's another finite state machine, and so on and so on. So the concept of a tree of finite state machines develops into behavior trees. The tree controls all of AI agent actions. Looks like a normal tree, so a graph without cycles. And nodes are evaluated pre-orderish because we go to the most left and most bottom node and start evaluating the tree from there. The nodes can evaluate into one of three states: success, failure, and running. Node type, there are several node types which I will show later, define how the children are evaluated and what are the possible answers. And when we go through the tree, the evaluation ends when root node returns its state. There are several basic node types. We've got actions. Actions just initiate activity. They cannot fail. They can only return success if the action is finished, or running if the action is taking place right now. We evaluate the tree every frame. So when the AI agent is doing something, like digging a hole, this is his action, and it would return running state. Then we've got conditions. Conditions are simple if statements. So they check the state of the agent or the in-game situation and can evaluate in success or failure, like every other if statement. Then we've got aggregates for evaluating children. Sequences, which is AND, logical AND. So we evaluate every child of the sequence node, and when one of them returns failure, we fail. And when every single node returns success, the sequence returns success as well. The opposite is OR node, so selector, which evaluates every child until one of them returns success. So it's like OR in the logic statement. And we've got decorators which can, for example, negate the node response or modify the behavior of child of the decorator. Example. This is a simple behavior tree that deals with combat situation. We've got the first node that we need to evaluate would be the most left one and most bottom one. So it would be enemy in sight node. It's a part of a sequence. So we need to, if the node fails, the sequence fails. And then we go back to the selector and evaluate next node because selector is waiting for success. So when we don't have enemy inside, then we target random location and move with the move action. But when we do have enemy inside, we need to evaluate the second child of the sequence, the leftmost sequence. And the child is selector, so we go to the enemy weaker node. If the enemy is weaker, then the node will return yes, and we attack. The action always returns true. So we go all the way up to the root, and the root evaluates the true. And if the enemy is not weaker, then we go to the sequence returns false, and selector evaluates another node, and so on, and so on, and so on. The advantages of behavior trees is that programmers only need to implement nodes, not the connections between them. I mean, when you implement sequences and selectors and the tree mechanics, all the programmers need to do is adding new nodes, new conditions, new decorators, new actions. Everything else is defined by designers who define how the nodes connect, and with the usage of sequences and selectors, they can basically implement all the AI they need. Nodes themselves can be implemented in scripting language, which has an advantage that some designers are more than capable to write their own scripts, so they can now add their own nodes, but in most cases the nodes need to be well thought, well written, so it's mainly done by trained programmers. They are easy to debug because always you can trace the decision chain of AI, because when you evaluate a node, you can always write in the debug what was the result of the evaluation and track all the process. It is very highly reusable because every node can be a behavior tree of itself, because the root node evaluates like any other node, so every node can be a separate behavior trees, which makes behavior trees, you can store library of behavior trees for reuse for another agent or even another project, because basic behaviors may remain the same. And adding new node types is not affecting at all the existing trees, so it's easy to expand the AI with new functionalities. And right now it is widely used in the games. We of course use it at 11-bit studios, and it's one of the best examples of using behavior trees is FIFA or NBA, like the huge behavior trees just to mimic the behavior of football or basketball player. But this does not come without disadvantages. First off, it's hard to understand and start thinking in the way the behavior trees work, because it's not an obvious way of making decision. setting up the whole setup, the whole mechanics of behavior trees might be complicated. The trees can be huge, like huge, with thousands of nodes just to reflect the whole behavior of an agent. We can, of course, fight with the size of the trees and with the evaluation time, because the bigger the tree, the longer it takes the computer to evaluate it, of course. And we can divide the evaluation into separate frame ticks, so we can put a time frame for the AI. So if it's more than, let's say, quarter of a frame of a second, then we skip it and go to other things and return the next frame. We can implement event-driven responses. So we do not evaluate the tree every time, like poking. What are you doing? Playing. What are you doing? What are you? No, we just wait for an event. I finished play, so reevaluate your tree. And of course, we can write the code better, so we can balance between the reusability of a node, and we can aggregate the smallest node into bigger ones, which would evaluate faster, but will lose the reusability. And that would be all for today about behavior trees and artificial intelligence. If you have any questions, I would gladly answer them. Thank you.